So we've looked at polar coordinates. We had just started looking at graphing polar equations, converting our polar equations into rectangular form so that we would understand or know about what the general shape was. We saw some equations and trying to recognize those equations in the shape. Now in this video, we're going to use symmetry to help us graph polar equations. So recall we could use symmetry to help us graph equations that are in the rectangular coordinate system. Using symmetry, it is just helpful in the fact that you know what it's symmetrical to, and we would have double the points knowing that it's symmetrical. So let's look at symmetry. So looking at the graph in front of us, it's on polar coordinate graph. Recall that positive x-axis, that was called our polar axis. This point right here that looks kind of like the origin, that is called the pole. And so notice that we rotate theta from our polar axis. We get our terminal side, and in here we have some point, which is our theta. So the graph here is symmetrical across this polar axis. Notice here, reflection, that terminal side across that polar axis, and we have this point right here. So in this case, our value is R. So you're still going R units. But our value of theta is going clockwise, so it's negative theta. And so if you're trying to test for symmetry across the polar axis, notice if you plug in theta, wherever we see a theta in our equation, the polar equation, and we get back the same R value, then it's symmetrical with a polar axis. So plug in negative theta for theta. And if R remains unchanged, then it's symmetrical to the pole. Okay, so let's look at another example of symmetry and how we would test for it. So looking at this next graph on our polar coordinate system, notice it looks like it is symmetrical across that line if we're thinking of the rectangular coordinate system across the y-axis. But that value, that y-axis, right, from our pole, that's sweeping it out pi halves. So it's symmetrical across the line. Theta equals pi halves. Let me go back and write that down. So again, this is symmetrical across the line, theta equals pi halves. So let's think about how we would get that. So notice right here, let's say that this angle from our polar axis, we're going up theta. So theta here, think of that to be symmetrical, it'd have to have the reference angle here of also theta. And so thinking about how I would get to that angle, we would have to look at theta pi minus theta. So that gives us the terminal side. Symmetrical. Across theta equals pi halves. So to test for symmetry, wherever we see a theta, we're going to plug in pi minus theta. So one other type, which is symmetrical to, so we kind of saw something symmetrical to, if it was rectangular, the x-coordinate, x-axis, if it was symmetrical to, in rectangular coordinates, the y-axis. Now think of it as across the origin. In this case, for our polar coordinates, it's across the pole. So if we have some point here, which is our theta, the symmetrical point across the pole is negative theta. And so to test for symmetry there, wherever we see an r, we're going to plug in negative r, and wherever we see a theta, we're going to plug in negative theta. If it's remained unchanged, then it's symmetrical across that pole. So I actually have this written out, typed out as this theorem for you. So for test for symmetry, if we're testing for symmetry across the polar axis, which we talked about looking like the x-axis. So in order to test for this symmetry in a polar equation, again, replace theta by negative theta. If an equivalent equation results, the graph is symmetrical respect to the polar axis. If we're looking at it being symmetrical to the line theta equals pi halves, which is the y-axis, then in a polar equation, we're going to replace theta by pi negative theta. If an equivalent equation results, the graph is symmetrical to the line theta equals pi halves. And to test for symmetry across the pole, which is like the origin for the rectangular coordinates, in a polar equation, replace r by negative r or theta by theta plus pi. If an equivalent equation results, the graph is symmetric to respect to the pole. So I misstated up here. We want to plug in theta plus pi, but this is the point negative r negative theta. But to get there, our reference angle here of theta, our reference angle here would be theta, but we're going from theta equals pi plus theta. So there's something that you need to note about this. These tests are great in the fact that if it works, then we have extra points, right? Double whatever we find those points, double that we would have. But these three tests for symmetry are sufficient conditions for symmetry, but they are not necessary conditions, which means that an equation may fail these tests and still be symmetrical across either the polar axis or the line pi halves or the pole. So let's look at some equations and let's test for symmetry. So the equation in front of us is r is equal to 1 plus sine theta. So let's look at this and graphing. So let's look at to see if this has a symmetrical across the polar axis. So again, to be symmetrical across this polar axis, if I plug in some value theta, I should get back that same value if I plug in negative theta for r. And so let's go in here and plug in negative theta for theta. So for the polar axis, again, plug in negative theta for theta. And so doing that, I get r is equal to 1 plus sine of negative theta. Well, sine of negative theta, sine is an odd function. And so sine again of negative theta, this is equal to negative sine of theta. Recall that cosine, just because we're probably going to need it, of negative theta, cosine's an even function, cosine of theta. And so this r is not the same thing of our original. So this is 1 minus sine theta. So this doesn't mean it's not symmetrical across the polar axis, but this test fails. And so it might not be symmetrical. Okay, so that was for the polar axis. Now let's look for seeing if it's across the line, theta equals pi halves. Okay, so if it's symmetrical across theta equals pi halves, that means that for some value theta, let's say that's theta, then it's going to be symmetrical. So our reference angle here is negative theta. And so it's going to be plug in pi minus theta for theta. And so looking at r, I have r is equal to 1 plus sine. So instead of theta, we're replacing that with pi minus theta. Well, my reference angle there is theta. Sine is, and it's in the second quadrant. Sine in that second quadrant is also positive. And so that is the same as sine of theta. So this r is equal to 1 plus sine theta, equivalent. And so notice this is the same equation as we have up here. So this tells me that it's symmetrical. Across theta equals pi halves. So if I find some point r theta on my graph, then I also know that r comma pi minus theta is also a point on my graph. So let's look at the pole also. And so for the pole, so recall we would plug in either negative r for r and see if that remains unchanged. Our equation was r is equal to 1 plus sine theta. If I plug in negative r for r, and I solve for r by multiplying each side of my equation by -1 to get r by itself, that's not going to give me the same thing. I'm going to get r is equal to -1 minus sine of theta. We normally don't put the negative on that side. Okay, so this test fails. Or we could take and plug in theta plus pi, or pi plus theta for theta. I can see that that's not going to give me the same thing. Doing that, I have r is equal to 1 plus sine. Instead of theta, I'm replacing that with this theta plus pi. Well, that's going to get me down into the third quadrant. Sine in the third quadrant, my reference angle is theta, but in the third quadrant, sine is negative. And so this would give me back r is equal to 1 minus, or equivalent to 1 minus sine of theta. So this test also fails. So we know again that it's symmetrical with the line pi equal, or theta equals pi halves. And so let's just graph this one really quick. And I think that we're going to call it for the week because I've been doing this for over a couple hours, which means you are watching videos for a while. So let me pause this. Let's, as I pull back up that equation and get us ready to graph this equation. Okay, so let's graph this now. R equals 1 plus sine theta. I put a chart here so that we could start plotting points. Let's plug in things that we know. And then because again, it's symmetrical across theta equals pi halves, which is the same thing as theta equals 90 degrees. That polar graph that I brought up has degrees, but we also can convert that into radians if you want. But let's just do this now with degrees, just because it might be easier to do this. So let's plug in values we know. 0 or 0 degrees. Sine of 0 I know is 0, so this would give me 1. And so plugging that in here, if theta is 0, I know that I also have a point at 180 degrees minus 0, or 180 degrees, or pi, and I would also have 1. So let's plot that. So when theta is 0, I'm not moving. I'm staying on the pole, and I have a point at 1. If I go 180 degrees, I also have a point at 1. I'm not 1. That's not 1, that's 2. So I also have a point at 1. So let's plug in another value. So let's say that we plug in 30 degrees or pi 6. So if we plug that in, we get that sine of 30 degrees is 1/2. So 1 plus 1/2, that is 3/2. So I know that 180 degrees minus 30 degrees is 150 degrees. And my R value is going to be the same, 3/2. So plotting that point there at 30 degrees, so going up 30 degrees, our R value is 1.5. And if we go 150 degrees, we also have 1.5. So let's plot another point, let's say 60 degrees. At 60 degrees, we get sine of 60 degrees is √3/2. So let's approximate that. And then let's also do 180 minus 60 degrees, which is 120 degrees. And so √3/2 is approximately 0.9. So 1 plus 0.9 is 1.9. Okay, so let's look at this. So starting here, we're going to come up and loop. And then at 60 degrees, we have about 1.9. So 1.9 is up in here. Symmetrical, it's about right here. And so we're going to continue here. Let's plug in pi halves. If we plug in pi halves or 90 degrees, sine of 90 degrees is 1, 1 plus 1 is 2. So 180 degrees minus 90 degrees is 90 degrees, so same point 2. So at 90 degrees, we're going to go up 2. So what about at pi? So if we plug in pi, or actually maybe we shouldn't do that. Maybe let's do 120 degrees. So 120 degrees, that is reference angle 60 degrees. So it's the same thing as this one plus √3 over 2, which is approximately 1.9. So at 120 degrees, we have about 1.9. So 180 minus 120, that's 60 degrees, which we already had. Do we have that? Thought we did. Yeah, which is 1.9. And is pi halves was 2. Things are a little off over here. I need to see this one line in here. Sorry about that. So that's 180 is 1, 150 is 3/2. So that should have been here. I knew something was off my graph. 120 is 1.9. So that's going to be right here. Okay, and so I don't think I have everything in there yet. Let's say that we plug in, just want to see about below this axis. And so let's say that I plug in 210 degrees. So 210 degrees. My reference angle is 30 degrees. Sine of 30 is 1/2. So 1 plus 1/2 is 1.5. Okay, so here I have 1.5. It's going to come back around. So it looks, I don't know if you can tell, but it kind of looks like as I zoom in, a heart. And this shape right here, r equals 1 plus sine theta, the sine value, so the heart is facing towards the y-axis, or theta equals pi halves. That's called a cardioid. It's a shape of a heart. So in front of us is the definition of cardioids. Cardioids are characterized by the equation of the form r equals a times the quantity 1 plus cosine theta, r equals a times the quantity 1 plus sine theta, or r equals a times the quantity 1 minus cosine theta, or r is equal to a times the quantity 1 minus sine theta. So if we're taking some value a plus or minus a sine theta, or a plus or minus cosine theta, a value is greater than 0, then we have a cardioid that passes through the pole. And so looking at this next equation, r is equal to 2 minus 2 cosine theta. This looks like one of those above. And so I know that looking at this, that I'm going to have a cardioid shape. So I could test for symmetry. I know that cosine theta is an even function. So cosine theta is the same thing as cosine of negative theta. So thinking about if I plug in negative theta for theta, what is that symmetrical to? So plugging it in again, we have theta here. And we plug in negative theta, it's just opposite direction. So this is symmetrical to the pole. Axis. So when I go about plotting points here, if r theta is a point, then I know r negative theta is a point. And so let's look at values that we kind of know. So if r theta is 0, if theta is 0, then I know my r value is 2 minus 2, which is 0. It's getting late. Negative theta, so 0, 0, that didn't tell me much. Okay, so I know axis. We have a point at our pole, 0, 0. So let's plug in another value. Let's say if we plugged in pi halves. We plug in pi halves, I know cosine pi halves is 0. So I have 2 minus 0. So I'm going to have a point at 2. So negative pi halves 2 is also going to be a point. Okay, so pi halves, which is 90 degrees and going up 2. Negative pi halves, which is at 270 degrees and going down 2. So let's look at 30 degrees. Actually, let's look at 60 degrees. 60 degrees is a little easier. And I'm writing them on the wrong side. So 60 degrees should go here. So that would be negative 60 degrees over here. 60 degrees, cosine of 60 degrees, I know is 1/2. So plugging that in, 1/2 times this negative 2, so that's negative 1. 2 minus 1 is 1. So I know I have a point going 60 degrees. I'm going to be at 1. And going negative 60 degrees, I'm also at 1. So let's look at what's going on at 120 degrees. So that's going to be negative 120 degrees. So 120 degrees, my reference angle is 60. But I'm in the second quadrant, so cosine is going to be negative. So I have 2 minus 2 times negative 1/2. So that's 2 plus 2 times 1/2. So that's 2 plus 1, which is 3. Just 3. So 120 degrees, I'm going to go up 3. 1, 2, 3. So at negative 120, which is the same as this line at 240, is also going to be 3. So let's look at 210 degrees. So 210 degrees, that's like a reference angle of 30 degrees, negative 210. So that's in the right here, positive 210, that's in the third quadrant, cosine's negative. So that's going to be 1 minus root 3 over 2. 1 minus root 3 over 2. So 1 minus about 0.8. But that 0.8 is times a negative 2. Gosh. So that's going to be positive, about positive 1.6 plus 2 is 3.6. I'm estimating. So let me just plug it in the calculator. One plus, so my 2's would cancel, so that was just really 1 plus root 3. Which is approximately 2.7. It was off on math. This is 2.7. Okay, so 210 was 2.7. So there's 1, 2. And then if I go negative 210, I'm in the third quadrant, which is 1, 2.7. 180 degrees. And I think we then have the shape. So 180 degrees, I know that cosine of 180 degrees is negative 1 times that negative 2 out front. That's positive 2 plus 2. So that gives me 4. It's going 180 degrees. I'm going to go forward, which looks like the heart shape. Something's off though. Because it doesn't look quite like a heart. So yeah, I was kind of doing things in my head. So let me go back and check my work. And while I check, I'm gonna pause the video. Okay, so this is actually 1 minus root 3, 2 times negative 2, which is plus, that's really 3.7. Which helps me because that gives me my heart shape, which I knew I should get. And so notice that this cosine one has the minus here. It goes towards the negative direction, x-axis, if we're thinking rectangular coordinates. Okay, so let's stop there. I'm not gonna finish this section this week. This is 10.2 again in our textbook. We'll look at other shapes that you'll get starting next week. So we'll finish 10.2 next week.